Welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell wherever it is. It's up there in the corner, I think now. Linear Algebra 1. We're doing Chapter 2, which is matrices. Section 2.6 is Cramer's rule. This lecture specifically, what we're going to do is use Cramer's rule to solve n-by-n linear systems as ratios of determinants. But there's a condition: we can't solve any linear system. Gaussian elimination is a more systematic method because it only happens when the determinant of the coefficient matrix is non-zero. Let's get to that. Before we state the theorem, which is known as Cramer's rule, what we're going to do is give all the notation and terminology we use in the theorem. Specifically, we want to use ratios of determinants, but determinants of who? Determinants of AIs or AJs, we're going to call them, and determinant of A. So who are all these guys? We're given a linear n-by-n system. The coefficient matrix is the matrix with all the coefficients set in front of our unknown variables. And then this constant column vector is the B1 to B2. It's classically the right-hand side of this system. What we're going to do with that is construct AJ. AJ is the matrix where we take column J of A, the coefficient matrix, and replace it with this column vector B. So we remove column J from the matrix and substitute it with this column vector B. From that, we create n other matrices. For each column, there's n columns in A, and so what we're going to do is we're going to create n other matrices, A1 to AN, and then the unique solution, if the determinant of this matrix is non-zero, it's going to turn out the unique solution is going to be the ratios of the determinants of these guys over the determinant of this guy. Let's state the theorem explicitly. Theorem, which is now known as Cramer's rule after Gabriel Cramer. What's Gabriel Cramer doing when he tries to cook up this thing? Torturing first-year students? No, that's never the answer. It's just a good application. What he's trying to do, I believe, is historically he's trying to find the equation of an ellipse through 5 given points or something like this. And so somewhere in that scenario, he cooks up viewing unique solutions as ratios of the determinants. In particular, Cramer's rule, before I start and state what it is specifically, I want to point out that Cramer's rule points out what should have happened in chapter 1, and when everyone says, I think I got horrible fractions, so I did something wrong. No, you didn't. When you get integer solutions, possibly you usually have done something wrong, because in most of the cases, you shouldn't have nice integer solutions, and the universe definitely doesn't care whether you get whole numbers. And this tells us that solutions to n-by-n linear systems are ratios of determinant, which means usually unless the determinant of A divides all of these other numbers, you're going to have fractions involved in the equation, even if the matrix itself doesn't have any fractions. What does Cramer's rule say? Cramer's rule says if you have a linear n-by-n system S, and you have the coefficient matrix A and this column vector B on the right-hand side, if the determinant of A is not zero, which is important, you can't solve all linear systems this way, only unique solution ones, and that's how you tell. If the determinant is not zero, it has a unique solution, first of all, is what it's saying, and then it explicitly gives you the solution as the ratio of determinant of A1 over determinant of A is x1, dot, 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 xn is the determinant of AN over determinant of A, where, in the previous scene I prepped you, but where AI or AJ is the matrix obtained from A by replacing the jth column of A with the vector B. Let's do this explicitly for a 2x2 and a 3x3. See, also from here, what you can see is to do Cramer's rule, what I have to compute is, and hopefully you watched the previous videos on how to compute determinants efficiently, because now if I do an n-by-n system, I have to compute 1 dot 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 n plus 1 determinants. I have to compute the determinant of the coefficient matrix, and then I have to replace one column at a time with this vector B, and then we have to compute the determinant of all of those guys, and then we have to take the ratios of the determinants. So to solve an n-by-n linear system using Cramer's rule, you have to compute n plus 1 determinants. This is extremely slick for 2x2 determinants. I have to compute 3 2x2 determinants. We're done. For 3x3, we already have to compute 4 3x3 determinants, which is going to be less fun. For 4x4, you get the idea. You better be good at computing determinants. Let's try this. All right, for example 1, we're going to solve a system using Cramer's rule, if applicable. What do they mean by that? The first step you should always do using Cramer's rule or in a system, check that the determinant is non-zero. If that's true, then you can keep going. What do we have with this system? This is a 2x2 linear system. My coefficient matrix A is going to be 3, negative 2, 2, 1, and B, if we need it, is 7, 5. Those are the two pieces of information from the theorem mumbo jumbo. Now I have my coefficient matrix, it's all numbers, and we have B, it's all numbers. If the determinant of this is non-zero, we'll cook up A1 and A2 and then find ratios of determinants to solve this system. The determinant of A is equal to 3, negative 2, 2, 1 determinant, which is going to be 3 minus negative 2 times 2 which is 7, which is not 0. Therefore, Cramer's rule is applicable. What do we do with that? Next step is you have to create n other matrices from the given one. This is 2 by 2 system. That means we're going to have to compute 2 plus 1 determinants. This is the first one. Then we have to compute 2 other ones, which will be A1 and A2. How do we get A1 and A2 from A? We replace column 1 with B, and then we create column 2 with B, and then compute those as determinants. That means the determinant, I'll write it like this, of A1 is I replace column 1 with 7, 5, and I leave the second column alone, -2, 1. This is equal to 7 minus 2 times 5, which is equal to 17. And the determinant of A2 is the determinant now of A, but I put column B where the second column was. That's going to give me 3, 2, and then 7, 5. This is going to be 3 times 5 minus 2 times 7, which is 15 minus 14, which is 1. What did we find? We found the determinant of A was 7, which is not 0, which tells us that we have a unique solution. The determinant of A1 was 17. The determinant of A2 was 1. What do we do with that information? That tells us our unique solution, x1, is the determinant of A1 over the determinant of A, which is 17 over 7. Try that with row reduction, and you're going to have fractions with 1/7. And that tells me immediately x2 is the determinant of A2 over the determinant of A, which is 1 over 7. This is the unique solution. Let's try this with a 3 by 3 system now. All right, example 2, we're going to solve a 3 by 3 linear system using Cramer's rule if applicable. What does that mean? Again, first we're going to compute the determinant of the coefficient matrix. If that's non-zero, then we can move forward. Computing the determinant of this, we have the determinant of A is equal to the determinant of 3, 2, 3, -2, -4, 2, 2, 0, 3, which is, if you want me to start actually using some rules or practice as I go along, I see I have -2 in all of these if I really want to, so that is going to be -2 times 3, 2, 3, which is 1, 2, -1, 2, 0, 3. So I notice I had -2 in the second row, so I have to multiply the determinant by -2 if I take that out. Now what I can do with that is, anytime I want, is possibly cofactor expansion. If I was going to cofactor expand, I would cofactor expand along this row because I have a 0 if I'm not going to do any other work to this, which I won't because I'm lazy. Therefore, this is -2 times, what are we going to do? Cofactor expansion says that we are going to have to, let me write that down here. This will be -2 times. Remember, when we're computing cofactors, I'm going to do this in my head now because I'm assuming you know how to compute determinants. I'm cofactor expanding along column 3. Go back and look at the previous videos if you don't know how to do this. What I'm doing is, in my checkerboard, I have plus, minus, plus, minus, plus. So it should be plus, minus, plus. This one I don't really care about anyways. So these ones are going to be positive coefficients. So 2, that's A31 times the cofactor, which is going to be this guy. If I block off column 3, or row 3 and column 1, I'm going to get times 2, 3, 2, -1, minus, technically speaking, but 0. And then we're going to get, I'll write it down just so you can see, but I don't really care. We're going to get, block off this and this, I'm going to get 3, 3, 1, -1. And then plus, we're going to get 3 times, we're going to block off row 3 and column 3, we're going to get 3, 2, 1, 2. What is that going to give us? That's going to give us -2 times. Here I'm going to get 2 times -2 minus 6 is -8. And then we're going to get plus 3 times 6 minus 2 is 4. So this is -2 times 12 plus -16, which is -4, which should be 8, which coincidentally is not 0. Cramer's rule applies. Let's move on to the next 3 determinants we're going to have to compute. Yeah, already 2 by 2, extremely slick. 3 by 3 already. Now, yeah, 6 of one, half a dozen of the other. We have now 3 specific methods for solving linear systems, especially when they're unique. We have Gaussian elimination, we have inverse matrices, and then now we have Cramer's rule, which is ratios to determinants. In Cramer's rule, the problem you can now see is we have to compute, for a 3 by 3 system, we have to compute 4 3 by 3 determinants. All right, the determinant of A1 is equal to, I'm going to cofactor along column 3 again, mostly because I have 2 zeros. This is going to equal Now, what are we going to get? I'm going to get 0 times I don't care, plus 0 times, or minus 0 times I don't care, plus 3 times, what are we going to get? Block off this and this, and we're going to get 4 to negative 12, negative 4, which is equal to 3 times 4 times negative 4 plus 12 times 2, which is 3 times negative 16 plus 24, which is 3 times, what are we going to get here? 8, which is 24. Let's compute the other two. All right, for the determinant of A2, this time, again, it looks like we're going to use the bottom row every time. I have 1, 0. Last time we had 2, and it was still a big number. Let's see what we get this time. This time we're going to get cofactor expanding along the bottom row is going to give me 2 times the 2 by 2 determinant, 4, 3, negative 12, 2, minus 0 times I don't care, plus 3 times the 3, 4, negative 2, negative 12. This one's a 0 immediately. There's no point writing it down, especially if you're on an exam. That's a time saver. This is now equal to 2 times 8 plus 36, looks like. And then this one is going to be 3 times, we're going to get negative 36 plus 8. If I did that right. Don't do it in your head. Write the steps down, but I'm a wizard, so I can do them in my head. I'll probably get them wrong that way. A wizard will still do that. This is going to give me 2 times 44 plus 3 times negative 28, which is 88 minus 84, which is 4. Next. All right, once again, the determinant of A3, I take column 3 and I delete it and I replace it with this column vector. And we're going to get, again, I got 2 zeros on the bottom row, so we're going to cofactor expand along row 3 again. And that tells me I'm going to get positive 2 times the 2 by 2 determinant obtained by blocking off row 3 and column 1, which is going to be 2, 4, negative 12, which is 2 times negative 24 plus 16, which is 2 times, what do I get? Negative 8, which is negative 16. Done. This tells me the determinant of A3 is negative 16. What do I do with this information? We write the unique solution as the ratio of these determinants. Given this information, that tells us that the unique solution is x1 is the determinant of A1 over the determinant of A, which is equal to 24 over 8, which is 3. x2 is the determinant of A2 over the determinant of A, which is equal to 4 over 8, which is 1/2, and x3 is equal to the determinant of A3 over the determinant of A, which is negative 16 over 8, which is negative 2, or the unique solution is x1, x2, x3 equals 3, 1/2, negative 2, viewed as ratios of determinants. Thank you, Gabriel Cramer. Please subscribe right here. I'll see you next time.